Medical Physics, Chapter 9, Light and Optics, and we're going more because we need to have some few more people, yes, to collect all the people here. Yes, and we are going to this course. Introduction of the light is something, yes, again the same like electromagnetic waves, electromagnetic radiation. It's a form electromagnetic radiation, light. The speed of light is the speed of the light in vacuum in this universe. It's 3 multiplying on 10 in the power of 8 meter per second. Yes. So it's everything what we have in this world, in this university, we compare it with the speed of light in the vacuum. Yes, with this universal mathematical and physical constant here. The light represents energy transfer from the source to the observer. Yes, and here on the picture it's a spectrum of light, visible light. It's very short range of our light wavelengths here, from ultraviolet to infrared wavelengths of the light, what we could see with our eyes, what is the possibility of our human eye here, from the violet to red. We just can see them, just can look at them, and it's with our violet it's nearly 400 nanometers. Blue one it's 500 nanometers. The yellow it's 600 nanometers wavelengths, and the red it's 700 nanometers approximately. Yes, and we couldn't see the infrared and ultraviolet part of the light spectrum, but it's a very narrow range of the huge range of these wavelengths. Yes, we have cosmic rays, the 10 in the power of -12 meter, gamma rays, X-ray 10 in the power of -9, yes, nearly 1 nanometer wavelengths, very hard radiation, ultraviolet nearly 1000 nanometer. We have infrared, microwave 1 millimeter micrometers, and the millimeter is something like radio radar, radio waves into nearly 1 meter wavelengths, and broadcast band it's nearly 1 kilometer long wavelengths. What is the nature of light? Yes, before the beginning of the 19th century, light was considered to be a stream of particles, something like that. Yes, so we are think about light like a stream, like a fluid of the particles. Yes, and we are thinking about the we could think about light like a wave out, like a park, like a source of waves. Yes, something like that. And during the 19th century, 20th century, the other point of view was very widely scientific basement during this, and in the view of our other developments in the 20th century, the light must be regarded as having a dual nature. So always we are thinking about the light Yes, something like have the dual nature. Oh my god, we are waiting. We are waiting for everybody. Yes, yes, I'm waiting. We have many few, not many absent people here. So we are waiting a little bit because everybody must be in the same conditions. Yes, that's why I'm taking a little bit of lecture of light. So we will have this part of the lecture during the this transferring exam or something like that, because our administration told me to do so. So we are waiting for everybody. Yes, and maybe 10 minutes, something like that. Yes, and then we will start again. Okay. And when we're talking about the nature of light, we always think about this dual nature, that light is the stream of particles, corpusculus, like we say in the Latin. Yes, and the force pulls this particle into medium, something like that. Yes, and some force pull this particle from medium, and this particle we will call them photons. Yes, the particles of light. And we are always will be think about the light like a wave propagation of something. Light behaves both as a wave and as a particle, both. Yes, very complicated nature of the light. It could be particle, it could be wave. Yes, and it behaves both. In some experiments of the light behaves like a wave. In some part of the experiments the light behaves like a particle, like the stream of particles. As a wave, it produces interference and diffraction. Yes, it's absolutely wave basement properties of this matter. And as a wave, it produces interference and diffraction, which are of minor importance in medicine. As a particle, it can be absorbed by a single molecule. Yes, it's something like the molecule or the atom absorb some particles. Yes, and give us the excited state of the particle, excited state of molecule. When a light photon, yes, this particle of light, or corpuscular of light, when a light photon is absorbed, its energy is used in various ways. It can cause electrical change. Yes, actually. And here that on our pictures we have the force which pulls particle into the medium, and opposite force that pulls particle from the medium. And don't forget that our particles is our photons, it's our corpusculus. And the wave of light, wave H bends at the entry and wave H bends at the exit, actually. And what happen? What can we? How we can imagine the small diffraction effect? It's a something what happens on the wide gap after propagation of the wave of light, of the wave. You could see of wave like something like propagation of the wave on the surface of the water. Yes. And the every point of the wavefront, I could say, could be a source of another wave. Yes, so the narrow gap give us very large diffraction effect, much more large diffraction effect than the wide gap. The small diffraction effect, rather small. So and the lower picture give us the difference between the constructive interference and destructive interference. So if we have two waves, yes, which have the same period, the same frequency, or they are oscillate in the same period with the same frequency, or this phase, shift of phase, are the same, so they could be constructive. So their amplitude, when they summarizate, the amplitude begins summarizing. So the amplitude could be a sum of the previous amplitude of two waves. If we have destructive interference, it means that we have two waves with the different shift of the phases, yes. So they are not coincide with this maximum and minimum of the wave, and so the result will be the line. So no big difference of amplitude. And this rays optic, sometimes it's called geometric optics. It involves the study of the propagation of the light. It uses the assumption that the light travels in the straight line path in a uniform medium and changes its direction when it meets the surface of the different medium. So we have two assumptions in this model. We have that light travels in a straight line path in a very uniform medium, yes, and it changes its direction only when it meets the surface of a different medium. Yes, the reflection and how it works. The reflection of the light. If the ray of light, the incident ray, travels in a medium, yes. So the incident ray, it's will looking like vector, yes, it's something like little part of the line with some direction. They meet the medium, yes, and we have this perpendicular. When our light meets the medium, this border of two mediums from one medium to another, when it encounters a boundary with the second medium, the part of the incident ray is reflected back into the first medium. Yes, it could be. It's a reflection. How we are just trying to make some formula of your reflection. There are two types of reflection. We have specular reflection, from the smooth surface, and the reflected rays here, it's parallel to each other. You have plane mirror, yes, and all reflection in this text is assumed to be specular. Yes, it's specular reflection. Actually, we are talking about them all the time. And so you have incident ray, you have reflected ray, and you have this range of angle of incidence, angle of reflection, and they are equal. They're equals to each other. Angle of incidence is equal to angle of reflection. It's one of the big basement rule of this reflection of light, simple optics. Yes, and the diffuse reflection, it's much more complicated case of the reflection. It's a reflection from a roof surface. The reflection rays travels in a variety of directions, so they have very complicated, no smooth surface. It's a rouge surface, yes. And this picture shows that this reflected rays travel in a variety of directions. A surface behaves as a smooth surface as long as the surface variation are much smaller than the wavelengths of the light. Yes, in that way. It could be a part of the reflection. It's a real diffuse reflection, but in this course we didn't talk about that. We are noticed that we could be a refuse reflection. It could be it's a reflection from a roof surface, but we didn't talking about that. And the law of reflection. It's a normal, it's a line, something like line perpendicular to the surface. Yes, in the incident ray, the reflected ray here, and the normal to this surface, a perpendicular line to the surface, they are lying, all these lines, incident ray, normal, and reflected ray, they are all lying in the same plane. In the same plane, like the plane of the this paper, the sheet of paper. It's something like plane. You can imagine like it's a Cartesian coordinate there. Yes, so we have only 2D, 2 dimensions, and all these rays and normal to the surface, to the border between 2 media, align into one plane. Yes, so they align on the sheet of paper, something like that. And the angle of reflection is equal to the angle of incidence. So people trying to investigate what they see when they look at the different experiments with the light, with the, Antony van Leeuwenhoek, he was the first who was trying to investigate, to work with the something like microscope. Yes, so he was in our European science, he mentioned like inventor of the microscope. Yes, so he trying to investigate or observe the drop of the something like water, but it was not distilled water, it was just water from the river. Yes, and he was investigated the water from the puddle. Yes, muddy puddle. It's something like that, and he noticed that river water, drop of the river water, if we have very big multiplication, he used the spherical lens. So we use the sphere of the oil drop of glass. Yes, and some mechanisms of the roots, mechanisms of the screws to make it move, this lens, and this special type of the microscope, the first microscope, showed him that he just known that the drop of river water there could be something like a very big volume of different organisms inside the water. So he noticed that in Fusoria shoe, yes, some very one cell organism like amoeba in Fusoria shoe, and some special type of the this one cell organism, bacteria or something like that. Okay, that's why we started again from the how all the basement law of this rules of the normal optic, simple optic, how it works. Yes, how this reflection relationship between the incident ray, reflected ray, and the angle of reflection is equal actually to the angle of incidence. Yes, it's a basement law of normal optic, of the basement optic. The incident ray, the reflected ray, and the normal to the surface, to the border of two media, are lying in the same plane, and this theta 1 equals to theta 1 prime. The relationship between these two angles, the angle of reflection and angle of incidence, they're equal. Yes, it is called, it is a relationship between two angles. It's called the law of reflection. Yes, the one of the basement law of our universe. Yes, it's also some simplification of reality, but actually it's really good works in some simple experiment. The multiplier reflection, the incident ray strikes the first mirror. The reflected ray is directed toward to the second mirror. Yes, there is a second reflection from the second mirror. Could be here on the picture, the lowest picture in the left bottom corner. There are multiplier reflections. Yes, so they are reflected from the one mirror, the first mirror, and the reflected ray is directed toward the second mirror. So this is the second reflection from the second mirror. And this retro reflection here, we can assume the angle between two mirrors, it's 90 degrees angle, and reflected beam returns to the surface, to the source, parallel to its original path. Yes, this is a phenomenon, it's called retrorefraction. It is used in different type of the science. Yes, it's a measuring of the distance. It could be, yes, for very famous experiments, it's measuring the distance to the moon, for example, because we have the reflected beam returns to the source parallel to its original path. If we have a good surface, yes, and the scientist trying to find this good reflected surface on the moon, and we could find that the reflection, the reflected beam from the surface of the moon returns to our source of the light beam. Yes, and we just need to measure the time what we need to have this, how much time the reflected beam need to return to the source. Yes, so the two ways, two distances are divided to the time, and we receive the velocity or the distance of the moon. The automobile taillights, yes, so we just can use it in everyday life, because the part of the mirrors are standing in that position that the reflected beam returns to the source parallel to its original path. Yes, traffic signals, yes, we widely use them. So we need to